Right? Suppose we have a yellow ball and I drop the ball. Okay, so if I drop the ball falls. Now the reason why the ball falls is because it has weight. It's pulled down by its own weight. All right. So the force, the force is the weight. Okay, I'll represent the force by F. Okay, it's actually we're gonna call it W for the weight. W for the weight. Now, so this object falls. Okay, suppose it falls for some distance. It falls for some distance. Maybe from there it falls to there. Let's say it falls by a distance of h. Now let's say at first it was at rest. It was at rest. Then as it falls, it goes faster and faster. It goes faster and faster. After falling a certain height, h. After falling this height, it has gained a certain velocity. It has gained a certain velocity. Let's say it has gained a certain velocity v. Okay. Now let's think about the energy. If you think about the energy, this v down here means that the ball has kinetic energy. When it was at first at rest, it has no kinetic energy because it's not moving. But now that it has a velocity, it is moving, it has kinetic energy, and this kinetic energy is given by the formula half mv squared. So that's our kinetic energy. Now, okay, I'll write down the name. The kinetic energy is what this is. But where does this kinetic energy come from? Okay, it comes from the weight pulling down the object. So by the weight pulling down the object gains energy. That's fine. So the weight is doing work. We can think of the weight as doing work. This weight it does work on the ball. So it's like something is pulling it down, like I'm pushing a ball along a table. When I do work, the ball accelerates. So the weight pulls the ball down, the ball accelerates. That's fine. Okay. Now, but surely, okay, the force does weight, but where does this energy come from? All right, the weight do the work, and then it gains the kinetic energy. But if you think of energy, we might think that energy has to come from somewhere, and we can say that it comes from the work, perhaps. But another way to think about this is that we can think that if we have a ball, okay, if we have a ball that is higher up, all right, that's higher up, then when it falls down to say the same level, it will have a bigger velocity and therefore bigger kinetic energy. So the greater the height that it falls, the bigger the kinetic energy. Okay, so we can think of it as if there's some kind of energy that is there, right? That is just there somewhere, just because the ball is at a certain height, right? Just because the ball is at this position that is higher up, it somehow has this energy. We can't actually see it because the ball is not moving, but it is there. And when we drop it, it shows up by changing to kinetic energy. So this vague idea, is described as it. Well, we can make it more concrete. We can actually try and put a number to it. But let me just write down the idea. This idea is called potential energy. The idea that if the ball is higher up, it has more energy. Okay, and this idea is called potential energy, and we think of this as some kind of an energy that is hidden there that we can't see, but when you release it, when you drop the ball, it changes into kinetic energy. But how can we put a number to this potential energy? What is the value? Now the way it is done is that this potential energy is normally written given the same value as the work that the weight will do on the ball when the weight pulls the ball down by this height. So if I think of okay, to make things maybe easier to visualize, let me think of let's say maybe roughly this as the ground level. Okay, let's say I have a ground level about here, so easier to visualize this. This is my ground, ground, G-R-O-U-N-D. So when the ball is at this height, okay, the weight will pull it down. The weight will pull it down. So to make it easier to visualize, let's say the weight is 10 newtons. Okay, let's say the weight is 10 newtons. 10 newtons, meaning that the mass would be 1 kilogram. 1 kilogram mass. Okay. Oh well, actually, might not be exactly 1 kilogram. So let's just say that the weight is 10 newton, and let's say that the height here is maybe 2 meters. Okay, 2 meters. So we normally say that the potential energy is normally written as to be equal to the work that it's the weights, the gravity will do on the ball when you release the ball. So this means that it is the work done by this weight over the distance which is h. Now we know how to find work done. So we are saying that the potential energy, okay, the potential energy is defined to be equal to this work done by the gravity. Now the work done by the gravity in this case will be force times distance. So force will be the weight, h is the distance in this case. So the force times the distance. Now we know how weight is related to mass. We know that weight is related to mass by the formula, write this down here. Weight is equal to mass times the acceleration due to gravity. So this is, we can substitute into here. So it's mg and h. So this is the usual formula for the potential energy. It is the work done by gravity as the gravity pulls the ball down by this height. Okay, so, and we sometimes use the short form PE for potential energy. Now we understand that when you do work on the ball, the work done that you calculate in this way, force times distance, the work done would actually be equal to this kinetic energy. Okay, if the ball starts at rest. So it will be actually equal to this kinetic energy, and therefore we can say that this mgh, this potential energy, is equal to the half mv squared. It's equal to the half mv squared, because we know that work done is equal to kinetic energy, as we've seen in an earlier video, and that's the kinetic energy. Okay, so this connection between the work done by the gravity and the kinetic energy leads to an important idea about energy. By associating this work done with a potential energy, what we are essentially saying is that we are, if you like, creating this idea. Right? We create this idea that this potential energy becomes changed to the kinetic energy as the ball drops. So as if the ball is higher up, like when h is larger, the ball is higher up, it will have more potential energy, and that value is given by this formula, mgh. So the higher the h is, the bigger this potential energy. And if you drop it, as it falls down this height h, it will all be converted to the kinetic energy. So the potential energy as the ball drops becomes all converted into kinetic energy, and according to this equation, they would be exactly equal. So this connection, this idea that the potential energy is converted exactly into the kinetic energy, leads to an important idea in physics. Let me write this down. It is the idea that that energy is conserved. Okay, it is called the law of conservation of energy. Right, and this law says that energy cannot be created or destroyed. Okay, it can only be converted from one form to another. Now this is quite a lot of meaning which are contained in these two lines, and as we learn more about physics, we will come to appreciate it more, because you would probably already know that there are many types of energy. Energy is not just the potential energy and the kinetic energy in this example. Those are the more obvious and simpler to understand form of energy. There are other types of energy, like heat energy, nuclear energy, elastic energy, and so on. But there are all these other kinds of energy, and the idea is that what we have seen here is that the potential energy can be converted into kinetic energy, and in this example, what we have seen is that when the ball falls, the potential energy will disappear because h drops to 0. Okay, the potential energy will disappear, but Although this potential energy disappears, it doesn't mean that this energy is destroyed, that it is gone or vanished. It just means that it's converted from this form, this potential energy form, to another form. In this case, the kinetic energy form. Right, so that's that's how this example illustrates, how this example shows this law of conservation of energy. And we can take it another step further. Before that, let me just mention that. So when the potential energy, let's say you find a certain value using MGH, when it's converted into kinetic energy, the kinetic energy the value of the kinetic energy must be exactly equal to the amount of potential energy that you start with when the ball is on top. So that's why we have this equation. All right, it's a very precise relation. The potential energy that disappeared when the ball falls down is exactly equal to the kinetic energy that appears when the ball now moves with this velocity. Okay. If you take it a step further, the ball, when it hits the ground, it will stop. So what happens to all the kinetic energy if it stops? By the time it hits the ground, there's no more potential energy. H is 0. No more kinetic energy. Ball has stopped. So what happened to the energy? Does that not mean that energy is now destroyed? Well, no. When it hits the ground, you hear a bang or a pop sound. All right, when it hits the ground, and if you have a very accurate thermometer, you'll measure that this area around the ground will become slightly warm. It might have gone up by a temperature of 0.01 degrees Celsius, for example. And that's heat energy.